this problem, we have a wakeboarder being towed by a boat at 18 miles per hour by an inextensible 75-foot rope. The wakeboarder accelerates out of the wake at a constant tangential acceleration of 3 feet per second squared. Our goal is to find the wakeboarder's velocity relative to the boat at 30 degrees from behind the boat, the velocity of the wakeboarder relative to the earth at the same position, the kinetic energy of the wakeboarder's face hitting the water if their head weighs 10 pounds and is 5 feet above the water, and finally, to solve for the velocity of the wakeboarder relative to the boat, we solve for their tangential velocity at the 30-degree position. Since we've been given a constant tangential acceleration, we can use the formula alpha is equal to a subscript t over r, where alpha is the angular acceleration, a subscript t is the tangential acceleration, and r is the radius, which in this case is the length of the rope. Knowing this, we can then use the formula omega squared is equal to omega naught squared plus 2 times alpha times theta, where omega is the angular velocity, omega naught is the initial angular velocity, alpha is the angular acceleration we just calculated, and theta is the 30-degree angle given in the problem statement. One thing to note is that omega naught is 0, so our formula reduces to omega squared is equal to 2 times alpha times theta. Solving for omega and plugging into omega is equal to v over r, where omega is the angular velocity from the previous step, v is the tangential velocity, and r is the length of the rope, yields the magnitude of the velocity of the wakeboarder relative to the boat, which is 15.35. Now that we have the tangential velocity of the wakeboarder, we need to break this velocity into components according to our coordinate system and add these to the components of the boat's velocity. Doing this yields the relative velocity of the wakeboarder with respect to the earth. Doing this gives us a velocity of 34.075 feet per second in the I-hat direction plus 13.293 feet per second in the j-hat direction with a magnitude of 36.58 feet. We can use this velocity to solve for the kinetic energy during the impact between the wakeboarder's face and the surface of the water using the conservation of energy equation. T1 plus Vg1 plus Ve1 plus the non-conservative work from 1 to 2 is equal to T face plus Vg2 plus Ve2, where T1 is the kinetic energy of the wakeboarder's face 5 feet from the surface of the water, Vg1 is the gravitational potential energy of the wakeboarder's face at 5 feet, Ve1 is the spring potential energy at 5 feet, T face is the kinetic energy of the wakeboarder's face at impact, Vg2 is the gravitational potential energy at impact, and Ve2 is the spring potential energy at impact. Since there are no springs involved, Ve1 and Ve2 are equal to 0. If we set the datum for this problem to the surface of the water, we can reduce Vg2 to 0. The non-conservative work from 1 to 2 also reduces to 0 because we know that the wakeboarder has to let go of the rope before impact, meaning there is only one conservative force within the constraints of this system. Making these substitutions, the equation reduces to T1 plus Vg1 is equal to T face, or 1/2 mv2 squared plus mgh is equal to T face. Plugging in our known values and solving for T face gives us T face is equal to 257.78 pound-foot. Solving for V face from T face can only be done by T face is equal to 1/2 mv face squared. V face squared is equal to 40.74 feet per second, which converts to 28.78 miles per hour.